Hi, just wanted to finish the lecture on rotational motion. So we started by considering an object going around in a circle of radius r and velocity v. The good news about rotational motion is it's very similar to linear motion. Everything we've learned so far, from position to velocity to acceleration, have their exact counterparts in rotational motion. So there's really no new concepts to learn, just a few more variables. So, for instance, if an object's rotating around, we can specify where it is in the circle by an angle. And this is similar to the position. So at an initial time t equals 0, it's at a angular position theta naught, measured relative to the x-axis. If the particle is moving counterclockwise, then it's positive motion. If it's moving clockwise, then it's negative motion. Suppose some later time t, the particle is at angular position theta, and the angular displacement would be theta minus theta naught. So let's write down some variables. For position, we have theta, which is measured in radians, and if the particle goes around in a full circle, then theta is 2 pi. For displacement, we would have delta theta, which equals theta minus theta naught. For angular velocity, we would have the time rate of change of theta, which is given by the Greek symbol omega, not w, but omega, and this is given in radians per second. Next, we would have the derivative of this angular velocity, given by the Greek symbol alpha, to give angular acceleration, measured in radians per second squared. So you see the relationship between angular and linear is a very straightforward one. You have basically the same kind of variables you would have in linear motion. Now we can relate the distance the particle travels, because we know that in 2 pi radians it does 1 full revolution, or circumference. Now if it travels less than that, say just an angle theta, then it would have subtended an arc length, say s sub t, given by, shown in this picture here, and given by the equation for the arc length. S sub t equals theta r, where t means tangential. Now we can take the derivative of both sides of this equation to get the tangential velocity, that is, the velocity along the circle. And so we have v sub t equals omega r. Finally, for the tangential acceleration, we would have a sub t equals r alpha. That's the tangential acceleration times the radius times the angular acceleration. Now remember, s sub t, v sub t, and a sub t are the displacement, velocity, and acceleration along the circle. That is the tangential motion. They shouldn't be confused with what you've learned so far about the displacement, velocity, and acceleration that is in linear motion. So now with these angular variables, theta, omega, and alpha, we can go back to basically all the equations that we've learned and just replace them, to replace the linear variables with the angular variables. For example, here are our familiar equations of linear motion. To get the equations for angular motion, you would replace every v by omega, every s by theta, and every a by alpha, and here's what you would get. Basically, the same set of equations. Okay, that's it for now. I'll see you next time.